Okay, so this is Availability Workbench. As you may know already, it's a modular suite of tools, so there are different tools available within that suite for different types of analysis. I'll pick through some of these different tools in order just to give you an idea of what they do, how they work, what kind of advantages they may bring for you. I'll start with RCMCost. This is a tool for assisting with reliability-centered maintenance. The main purpose of this module of Availability Workbench is to help you select and optimize a maintenance strategy. So if you're familiar with AvSim, you'll know it uses Monte Carlo simulation to simulate failure and repair and so on. RCMCost does the same thing, but it has more of a focus on maintenance rather than availability. So, okay. What I'll do is I will show you some examples of that. So I'll open an example project. So on the left-hand side, you can see we have a sort of functional location hierarchy, a hierarchy of blocks, essentially a functional familiar that shows you the hierarchical relationships between your systems and equipment, the functions and functional failures of those equipments, and the causes of those failures. So, for example, I've got a block here that represents a plastic extrusion unit with a child block beneath it representing a screw feeder, an equipment that's part of that system. These blocks can be added to a hierarchy very easily. In the Add menu, you can add new locations that represent those systems and equipments. Beneath those locations, you can add functions, functional failures, and causes. So here, for example, beneath the screw feeder, I'll show you the data that's in there. There's the name of the screw feeder. I can enter a description and other text information. Beneath that, I can create a function. So one function of the screw feeder might be to contain the mixture. If I open that, you can see actually the function is a very simple object. It just describes what the parent equipment does. Beneath that, I can define a functional failure or multiple functional failures that might affect that function. So I open that. Again, it's just a simple description of how the equipment might fail to perform that function. And then at the root of the hierarchy, beneath the functional failure, I can enter information about the cause of that functional failure. So if you're familiar with the RCM process, you'll be familiar with this idea of selecting your equipment and then defining its functions, defining the various possible functional failures associated with those functions, and then the possible causes of each of those functional failures. Now, in RCMCost, the bulk of the information that goes into a project goes into that failure cause. It's this cause, that's where the program primarily performs the simulation. So I'm going to open up the cause. Now, I think you said you were at least a little familiar already with AvSim. If you are, and you've used AvSim before, and you've built what we call failure models in AvSim, then the properties of a cause might actually be quite familiar because they are very similar. To show you what I mean, if I first of all go to the failure tab, here is where I can define the failure information associated with this failure cause, a lot like I would with a failure model in AvSim. So I can enter that data manually, choose a failure distribution that I expect that failure cause to follow, and enter the relevant failure parameters. But I can also use historical failure data. Now, Availability Workbench, both AvSim and RCMCost, are supplied with a viable analysis tool that's included with both of them. The viable analysis tool allows you to import historical failure data and use that data as part of your simulation. I'll be able to show you that a little later. But basically, you can import that historical failure data, do a line fit to the data, and the results of that line fit can then become the input data for your simulation. So your simulated failure should behave like the failures you've been observing in your real system. If you don't have that information, and in fact you don't have much data at all about the failures beyond your own judgment and what you know about the system, then you can also use the distribution wizard, which is this button, that allows you to build up an approximate bathtub curve or failure rate curve based on what you know about this failure, or what you can basically make an estimated or an educated guess about how you expect that failure to behave. So you can model one or two or all of the different regions of the bathtub curve, and for each of those regions you choose, you can enter estimates of the relevant parameters, like what's the random failure rate during the random failure period, at what point does the equipment begin to wear out, and so on. From that information, the program can build an approximate failure rate curve to mimic that behavior. So you can enter this information that will tell the program the failure behavior that the cause follows. And of course, later when we're simulating this cause, that data will inform how that failure behaves in the simulation. Now, obviously, you can also simulate repair and maintenance along with that failure. When you create a cause, automatically there will be a corrective task associated with it. And you can enter information about how long that repair will take, how much it will cost. You can even include details about the resources that are required. Now, I think you mentioned before that you'd only really been using AvSim as an availability tool, and that basically demonstrates that Availability Workbench, while you can enter a lot of detail about your system, if that detail is not available, that doesn't prevent you from making use of the tool. You can just provide what information is available and just build a simple analysis from there. It's the same with RCMCost. You can input information about things like the labor and the spares that are required for your maintenance, but you don't have to do that. If you don't have that information, the program will not give you an error saying that there are no spares. You can simply run without them and just get a more simple output from the analysis. But of course, as I mentioned, if that data is available, you can add things like labor and equipment. So, I can create new labor categories, tell the program about how long it takes this person to reach the site of the repair, how much that will cost. Similarly, I can create and add spare parts, and the spares let me tell the program about how much it will cost to buy a new spare. At level 1 and 2, I can tell the program about storage. These represent on-site and off-site storage. How many spares I can store locally, how many spares I can store to a remote location, how much will that cost, how long will it take to get the spare out of storage to use in my maintenance task. At level 3, which represents the supplier, I can tell the program how long it will take to get a new spare in the event that I run out. You'll notice there are a lot of grayed out fields here. These are fields that are only used by AvSim. RCMCost does not use these fields, which is why I can't do anything with them here. So I can add spares to my list of resources. So during the simulation, if there is a failure and it triggers a repair, then we will get all of the costs and all of the delays associated with the resources that we need, and we'll actually be able to see a breakdown of that in our results later on as well. So I can build a pretty detailed picture of the repairs that I perform to fix these failures, but I can also build a detailed picture of the preventative measures that I take, scheduled maintenance, so things like, say, scheduled replacements, lubrication, condition inspections, and things like that. So let's say I'm doing proactive maintenance. Maybe it's something like lubrication, for example. I can create one or more planned maintenance tasks. You'll notice that for a planned task, a lot of the data is similar to a corrective task, but now you'll notice there is also an interval where I can tell the program how often this maintenance takes place. Am I lubricating this machine every 6 months, or am I just replacing it every 5 years? I can enter that information, and again, that will have an impact on my final result. And also, as we mentioned at the beginning, the main purpose of RCMCost is to help you choose and optimize a maintenance strategy. We will be able to optimize this maintenance through RCMCost as well, work out what is the best frequency with which this maintenance should take place to minimize cost or downtime. So again, I can enter information about the duration and the cost and the resources associated with this maintenance. And then that gets added to my maintenance strategy for this failure. As I mentioned, it's not just that proactive maintenance like lubrication and replacement that we can model. We can also model inspection. So you can see here I have an inspection in my model. Inspections can actually perform two different functions in RCMCost. One is a fault-finding inspection. So if I have a failure, which I've marked as being dormant, meaning it's hidden, so I don't know that that failure is there until I check for it, then I can have an inspection, and that inspection has a probability of detecting that failure and triggering a corrective maintenance task in response. On the other hand, I can do condition monitoring, do a condition inspection where I can check my equipment while it's still working and look for signs that failure might be imminent. So that might be like a vibration inspection or checking for hot spots or cracks in a casing. And then if you spot that there's a problem developing, you can stop it from causing an outage by maybe intercepting that failure before it happens. So if we have a look at that, you'll see that actually most of the information here is exactly the same as a scheduled task, exactly the same as the planned task, but there are a couple of differences. One is you'll notice there is no spare button. There are no spares for an inspection, of course. All we're doing is checking the equipment. The other is that there is a predictive data tab. Here, if I'm doing condition monitoring, I can tell the program how far in advance of failure can I pick up a problem. So maybe let's call that 2 months. I will do that in hours. I can say, how does that probability change over time? So I might say it's just constant. And I might say, the total probability of detecting that failure before it happens is 99%. So I can model that inspection as well. And what I'll show you is that as well as optimizing the maintenance that you're doing, you can also test alternatives and see if maybe there's a better potential strategy there for you as well. So there we've looked at some of the tasks that you can model in order to maybe detect or prevent failure. You can also model some other strategies as well. Things like the condition alarm, for example, performs a similar function to the condition inspection, only now instead of inspecting at regular intervals, the alarm can monitor your equipment continuously and then trigger PM in the event that maybe a failure is imminent. And you can model the costs associated with that as well to determine whether installing an alarm is a cost-effective thing to do. You can model commissioning. This is useful if you have a piece of equipment that follows a bathtub curve and is maybe prone to early life failure. You might decide to do a few months of commissioning to maybe pick out all of those early life problems before you get into the useful life of the system. Again, you can model the cost of that commissioning and see if it's worthwhile. Finally, you can enter the cost of a redesign. You could build a second model based on your first with some modifications made representing changes to the design. You can include the cost of those changes and then try to work out which of those two models predicts the highest or lowest cost. Is your redesign cost effective enough that it absorbs the cost of that change that you've made? So what I'll show you now is a little bit of how some of the, before I get on to the optimization, there is one thing that I haven't mentioned, and that is the effects. So up to now, we've talked about failure and repair and maintenance. We've talked about the cost of the repair and the cost of the maintenance, maybe through the resources and other things, but we haven't really talked about the cost of the failure itself, maybe in terms of lost production or regulatory fines and things like that. Effects, you'll find on the Effects tab here. You can see there that I can define effects in my project, things like maybe fire or loss of production and so on, and then I can attach those effects to any causes that might be expected to trigger them. So here, for example, this casing leaks failure might trigger a small loss of production and also material leakage. I can add another effect, choose from the effects that I have defined in my project, and tell the program what types of outages it applies to. So, for example, maybe some loss of production effects might apply to outages for maintenance, not just for failure. So again, when we're simulating the failure of this equipment, any failures might be able to trigger the effects associated with that cause and then accrue the costs and severities associated with that. But now let's take a look at the Strategy tab. So let's say I can open up my maintenance from here. Let's say I'm currently doing preventative maintenance. I'm doing planned maintenance once per year. So you can see planned maintenance is enabled and the interval is 1 year in hours. I'm going to click the green button and that will simulate this failure and tell me a little bit about the expected parameters associated with that. So here, for example, we can see the expected cost over the lifetime is about 6,000. We're getting criticality values, again, coming from the effects, estimated downtime, and a variety of other parameters. But the one I'm most interested in here is the cost-benefit ratio. This is the ratio between the cost of this cause with the maintenance in place, basically this value, and then the cost of this cause if I allow it to run to failure. Obviously, I want that value to be less than 1. I want the ratio to be less than 1 because that would indicate that having the maintenance is more cost effective than simply letting the equipment fail. So we can see that that's pretty good. It's quite a relatively small number. The cost of running to failure is maybe 3 times as much as the cost of doing this maintenance. However, we might be able to improve on that. So we can select our maintenance task, click interval optimization, and then we can tell the program we want to try 50 potential maintenance intervals. The first interval will be 1 month, and each subsequent interval will be 1 month longer than the last. So what will happen is, when I run the analysis, the program will simulate this cause and do the maintenance every month. It will store the cost of doing that, and then it will repeat that simulation, but with a maintenance interval of 2 months and store the cost of that. Then it will try 3 months and 4 months, all the way up to 50 months. It will plot the interval against the expected cost, and what I want to see is a minimum, basically a nice balance between paying too much because I'm over-maintaining and then paying too much because I'm under-maintaining and seeing a lot of failure. So I'm going to click OK, and I will run that. And there you can see the recommendation. This blue trace is the cost, and there's a nice minimum just there at 6 months, indicating that the cheapest maintenance interval for me will be to do the maintenance every 6 months. if I do it more frequently, I'm over-maintaining and paying too much for my maintenance. If I do it less frequently, then maybe my system becomes more likely to fail, and I get extra costs because of that. The other three traces are criticality that are being calculated from the severity values that I can provide in my effects. It is actually possible for me to tell the program what the maximum criticality values are that I'm willing to accept, and then the program can make recommendations to me accordingly. However, I'm happy with the interval I've got here, just there. I will click accept recommendation. That will update the interval. If I run again, you can see the cost benefit ratio drops. So now instead of about 33%, it's only about 23%. So I could cut out another 10% of the cost of running to failure by doing my maintenance more frequently. So that gives you an idea about optimizing a single maintenance task. Now, often you won't be working with just one task. You'll be dealing with a maintenance plan, basically a group of maintenance tasks that might all be performed together, maybe by the same class of engineer, or because they're all associated with the same area of a facility and things like that. You can model that kind of behavior, you can model that kind of maintenance in the form of a task group. You can create a task group, allocate multiple scheduled maintenance tasks to that group, and then optimize that group as a single entity. So you're not limited just to optimizing a single task, you can optimize groups of tasks as part of a single overarching strategy as well. So we've looked at optimizing maintenance for a single cause, and we've looked at optimizing maintenance for a task group. Now there is another type of optimization that RCMCost can do as well, and that is to optimize spare parts. So we saw earlier, if I say have a look at my spares here, I can say how much a new spare will cost, and I can say how much it costs to store spares as well. But I can also tell the program how many spares I can store, how many spares I can store locally, how many spares I can store remotely. I might want the program to recommend to me how many spares I should store in order to minimize storage costs, but also minimize outage costs. I don't want additional outages because I'm having to wait around forever for spares to arrive from my supplier. So I'm going to change the view here to show me spare optimization. I can choose a spare I'm interested in. I can tell the program, I might want to try storing between 0 and 5 spares locally, and maybe 0 and 5 remotely. I can run that, and you can see that the program is recommending to me that I store 1 spare locally, but I don't store any remotely. So that corresponds to this bar here, and you can see it's basically balancing between the blue part, which is the cost of storing my spares, and the pink part, which is the cost of downtime. So of course, if I don't store any spares, I have a lot of downtime because every time if there's a failure, I have to wait for a week or a month for the supplier to send me more spare parts. At the other end of the scale, if I store a lot of spares, storage cost is very high, as you would expect. So again, this is helping me to get the balance right between storage and outage. So finally, we've looked at a few of the different individual types of analysis the program can do. But of course, what it can also do is perform a simulation of all the causes in your project and just get an aggregated expected result for your model. So I'm going to click Start Simulation on the toolbar, and that will basically simulate all of my causes, and at the end, give me the overall results. So Here, for example, if I click that button, I can get the cost breakdown for my entire hierarchy. So it will take the cost of my system and break it down by labor and spares and various other driving factors. I can see availability data for the individual causes in my hierarchy. I can see occurrence information for my effects and usage information for spares and for labor. So I can see how many spares I expect to use and what that will cost me, how often I expect to call out my different engineers, and so on. And naturally, there will be lots of nice plots to show this information as well. So one nice example is a cost profile that can show me a cost breakdown across the life of the system, or maybe even the contribution plot that can show me the contribution of each cause to various different parameters, cost, downtime, and so on. So one of the things that's also worth mentioning is that this module can work in conjunction with AvSim as well. In the Tools menu, you can convert your functional locations into a simple block diagram in AvSim. And when you do that, the causes in AvSim will be linked by these data links to the new failure models in the AvSim module. So that helps you keep your failure data up to date between those two models. So that's an overview of RCMCost. Now I'll move on to some of the features of AvSim next. But before I do that, do you have any questions about RCMCost?
Yes, I have a question. For example, we saw that you can model one single failure. For example, my question is, if I have two pumps, for those pumps, I set preventive maintenance. How the program knows that the maintenance, the preventive maintenance will be performed at the same time or one before the other? I don't know if I explain myself. So
in RCMCost, each failure is treated independently. So there's very little or maybe even no interrelationship between the causes, except maybe some elements of shared spare parts. However, if you wanted to model that in more detail, it would be better to do it in AvSim. That way the program can model in more detail shared resources and things like that. The other thing that AvSim can do is it can model rules. The rules will allow you to inhibit or trigger maintenance based on the status of another block. So you could say, okay, if block X is under maintenance, then the maintenance of block Y should be prohibited until that maintenance on the first block is complete, just to make sure that you don't get a system outage because you're maintaining both pumps simultaneously. So I think what you're describing is better modeled in AvSim than in RCMCost.
Yes.
But maybe I can show you a little bit of that here, because it sounds like if you have been using AvSim, maybe it's not, you've not been using all the features that are available. Let me see if I can dig up an example that might be useful here. If you hold on for a moment, I will just find that. Yeah. So this is AvSim. I think you said you've used it a little bit before. Basically, as you'll know, you can build a reliability block diagram to represent the reliability relationships between equipment in your system, then simulate the failure, repair, and maintenance of those equipments, and get estimates about the availability of the system and the various subsystems as well. Now, as I mentioned, each of these blocks can represent a piece of equipment or even an individual failure mode of that piece of equipment. And those blocks can have an associated failure model. you can see I've got a list of models that I've created here. If I edit that model, again, you'll recognize that actually the data in a failure model is very similar to that in the RCM cost causes. It's just the same failure, repair, and maintenance information. So you can see here the model for, say, maintaining a pump and so on. Now, of course, the big difference between RCM cost and AvSim is that where RCM cost treats the failures independently, in AvSim you have the block diagram that lets you define the relationships between the equipment. So here you can see I've got 3 pumps in parallel, so my system would only be out of service because of the pumps if all 3 pumps were to be out of service simultaneously. So that's a fairly easy thing to model. You know, I have blocks in parallel with failure and repair data, but I can go into much more detail than that as well. So if I were to open a block and go to the Rules tab, one of the things I can do is tell the program the standby mode. This means that if a block is not in use, if the pump is not being used, it will behave a different way than if it's operating. In the case of cold standby, it means that the pump cannot fail and will not wear out. I can also have warm standby, which means the block can wear out and it can fail, but will maybe do so to reduce the rate because there's less stress on it. I can have hot standby, basically meaning the pump is behaving as if it's operating continuously. I can also define the maximum throughput of that piece of equipment. By default, that will be as a percentage. So I might say each of these pumps can carry 50% of my product through the system. And then I would only need 2 of those pumps to be working in order for the system to be operating at full capacity. And then, of course, that would mean that the 3rd pump could sit in cold standby until it's needed. So if one of the other blocks fails, then the pump will come online to compensate. As you can see, I've actually changed the units here from percentages to meters cubed per day. I can do that in the options for the program. If I'm not interested in using percentages for capacity, for productivity, I can use a unit of my own choosing instead. Now, one of the things that you will see throughout AvSim is this concept of rules. So you can see some here for the blocks. What I'll actually show you, though, is maybe I'll show you the rules for a maintenance task, because I think that's related to what you were asking earlier. So, for example, if I go into the pump, let's say, I take a look at the planned maintenance for a pump, you'll see that unlike in RCM cost, now there is a rules tab as well. I can add a rule, and for a task, that will let me trigger or inhibit a task under different circumstances. So I can trigger or inhibit a task by phase. This means that I can break the life of the system into different periods, which I can do here under phases. And then I can say, this task is not allowed to happen during phase 1, or this task will be triggered at the beginning of phase 2, and things like that. But I can also do this based on state. So I could say, well, inhibit this task if pump 2 is out of service, meaning this task cannot happen if the pump is not, if one of the pumps is not running. Now, I think also I could probably do something similar at the block level as well. If I go into the block, go to rules and add, you can see there are a lot of different rules here for blocks as well. One of which is set non-maintainable by state. So I could say, if pump, say, so I might say, well, set pump 1 to be non-maintainable in the event that pump 2 is out of service. So that will stop pump 1 from going into maintenance if pump 2 is already out of service. So it prevents that scenario where all of your pumps are down at the same time. So that's one of the more complex things that AvSim can do. And there are rules throughout AvSim for various different things, changing the maintenance behavior, the block behavior, the costs of different types of outage. All of these things can be modified based on a phase of operation, or in some cases, on the state of another block in the system. So speaking of the cost of outage, as you'll know, you can attach a failure model to a block, and that failure model can have maintenance associated with it. That maintenance can have resources and costs. And of course, when you simulate the model, when you run the analysis, you'll get an estimate of the overall cost from all of that failure and repair and maintenance and so on. But again, we haven't really talked about the cost of the outage itself. In RCMCost, that came from the effects. In AvSim, it comes from the consequences that you can see here. So I can create consequences that will model the cost of a complete failure of a system, but also the cost of a partial failure of a system as well. This consequence, for example, is a total outage consequence, and I can tell the program that if the associated system fails, it will cost this much per hour while the failure continues, but I can, if I wish, include the one-off cost of that failure as well. That consequence I've actually attached to my main system level here. So this is not a block in my diagram, this is actually the sort of header for that diagram. So if I double click, you can see there's the consequence. So if this system fails, it will trigger that consequence. But I can also have a loss of capacity consequence. This models the cost of a partial failure or degradation of my system. If I go from 100% productivity down to 90% or 70%, what will be the cost of that? Here you can see I can enter the cost per unit time of a unit loss of capacity from my system. So I can see the cost of lost production as well as the cost of outage. So if you wanted to model just availability, you can build the block diagram as we've done here, populate that with MTTF and MTTR data in the failure models, and just run it, and you'll get straightforward basic availability data. But as you've seen, it's possible to layer more detail onto that. You can include the cost of your resources for maintenance, the cost of the consequences. You can add rules that modify the way the block diagram behaves in different scenarios and get a really detailed model of the behavior of your system. So I'm going to run an analysis now of this whole system. You can see the progress of that at the bottom. I've told it to do 1,000 lifetime simulations. And here you can see, just like before, a breakdown of the costs of the system by various different driving factors. I can see availability data for my main system, but also for the subsystems as well. These are blocks with their own internal block diagram structure, and I will get availability data for them too, downtime information, capacity data, and so on. I can look at the information from my individual component blocks. You know, if I wanted to know what's the expected downtime of a pump, I can get that information. I can get the occurrence data for my consequences, a lot like I saw for the effects earlier. I can get a cost breakdown by phase, so I can see the costs between years 1 and 3 and the cost from year 4 to 20 coming from my phases that I've defined over here. And again, as before, we get information about how many spares we've used, what that costs, how often we're calling out our engineers, and so on. And we get plots as well. So I can go to plot, and I can say, take a look at the cost profile. I can take a look at contribution. This is a useful one, again, because it's helping me to improve my system design. I can look at that and say, okay, obviously this part of my system is causing some problems. Maybe I need to redesign that, introduce some redundancy, or buy better spare parts or something like that. Now, perhaps one of the most useful aspects of AvSim is that it lets you compare different projects together. RCMCost can do this too, but I feel like it's a little bit more useful in AvSim in a sense. So if I open up a different version of this project, so I'm going to run an analysis of my project. Again, you can see it's just working through the simulations. I will take a look at my importance plot, and I can see, that maybe there's some kind of problem with the column flare that I might need to improve. So I might just save that, open my redesign project, and maybe I've done something to improve the flare in here. I've improved the mean time to failure, or I've introduced more redundancy or something like that. So I can then go and find my original project, attach it as a library. So that's going to actually cooperate. So I'll go and find the original version of my project, and open that as a library. Now, the library facility, the main purpose of this is it lets you copy data from one project to another really easily. The reason I'm using it is that I can actually compare the costs of multiple projects if I attach them together as libraries. So I can actually go to the project comparison, and I can see that the upgraded version of my project, this redesigned version, which is I've called upgrade, actually has better costs. I've included the cost of the redesign. That upgraded project has an extra cost in it because of the changes I've made. I've added that to my project as well, but I can see that the lifetime cost of this upgraded system is expected to be substantially less than that of the original design. So I can use this to help me justify potential changes to my system design as well. So I can change around my block diagram, change some of the data, save it as a new project, run both of those projects, and then compare the results and see, is the modified project giving me a better result than the original? Should I make that system change or not? So that's an overview of AvSim. Now, there are a few sort of little modules alongside that I'd like to give you a sort of an introduction to. But before I go on to those, do you have any questions about AvSim?
Yes, I have two questions. For the results, can we have the results in export to Excel file, for example? I need the availability year per year. Is that possible?
Yep, so there are a couple of options available to you. One, of course, is simply use the Excel export facility. So you can find that in the File menu, and you can export pretty much everything from your project into Excel. So you could export your results, you could export your failure model data, your spares, and you can import most of that information as well. So if, for example, you have a bill of materials in Excel, you can import that into the program to save you the time of entering it manually. But yeah, you can export directly to Excel, but perhaps a better way of getting your results into Excel would be via the reporting facility. So the report facility allows you to open a report template which will populate with data from your current project. and we provide a variety of templates with the software, but you can create your own or customize the ones we provide. So I'll show you an example. So I see it in here. So to take a look at AvSim predictions, let's say that's probably the one you would look at, and you can look at, say, system availability predictions. So I can open that. So here's okay, that's probably because I need to update this report for this version of the program. Let me open a different one. See if that's using, probably I should open the, yeah, so basically this is, I think it's just because this version of the program is using a different version of the report designer to the one I'm trying to open. So but you'll be able to basically get the report that you can see here. You'll have a list of your systems, unreliability, capacity, unavailability, number of outages, amount of downtime. And again, this is completely customizable. So if you prefer availability to unavailability, you can output that instead. But yet, once you have that report, on the toolbar here, you'll be able to export it to Word, to PDF, and to text files. And this CSV, of course, you'll be able to open in Excel. So those are the two options you have, either reporting or the direct Excel export.
Okay. And the other question is, we need to model sometimes our tank level. That's a difficult one. You can modelize.
Yes. So if I'm interpreting what you're saying correctly, so I guess, are you looking at sort of like a temporary redundancy, whereby, you know, so you're looking at the tank emptying, and once it's empty, then the system is out of service, something like that?
Yes.
Okay, yes, then we can model that. I've actually got examples of it here. In fact, there's a better example. If I show you that one. So there you can see I've actually got a block called tank. This block can provide 24 hours of redundancy for the compressor. So once it's empty, then the system will fail. If I show you the failure model associated with that, you can see it's a special buffer model where I can tell the program how long it takes for the buffer to empty and then how long it takes for the buffer to refill again afterwards. So I think that's how you would be able to do it.
Okay.
So there are a few more sort of smaller modules I think I can show you in the last few minutes. One I mentioned earlier is the Bible module, which is supplied with AvSim and RCMCost. This module will allow you to import historical failure data, either in the form of a list of times to failure or replacement, or in terms of installation and failure date, or installation and replacement date. The program will automatically plot that information on a cumulative probability plot, time to failure against estimated unreliability, and then you can fit that data with one of a variety of failure distributions. And as you can see, I've fitted this data with a 2-parameter variable. There are the results, the expected lifetime, the shape parameter telling me that we've got wear out. And I can basically go back to, say, AvSim and say, for a valve, we go to AvSim, I look at the check valve failure model. On the failure tab, I've chosen the Bible set valve, and that's just pulled in the result of that Bible analysis. So these failure data that you see here have been estimated from the real failures I've observed in my system, and I can now use them as part of my simulation. So that module is just provided with AvSim and with RCMCost, so that's not an additional license. There are a couple more that would be an additional license. The first of those is the LCC module. The LCC module, or Lifecycle Cost, is a relatively simple one. Obviously, AvSim and RCMCost can already do an element of Lifecycle Cost, but where they're looking at the cost of failure and repair and maintenance, they are not looking at the cost of overheads. So things like power consumption, annual salaries, these are things that are not included in your maintenance strategy, but you can include them in the LCC module. This works by allowing you to define your own cost variables and then combine them with costs coming from the other modules using cost nodes. So each cost node that I've created can have a cost equation in it. I'm combining my own global variables, like say senior management rate and junior management rate, with cost variables that I can take from AvSim or from RCMCost. So I could say I'm going to add to that something from AvSim. So I'll go A dot, and I say from AvSim I want to add my total labor costs. I double click that, and that gets added to my equation. So now when I analyze my cost hierarchy, these equations will combine together the costs coming from AvSim or RCMCost with my own cost variables. So I could, as I'm doing here, take the annual salaries of my management team and add that to the overall labor costs over the lifetime and get the total labor cost based on both of those values. So I can get a much more detailed lifetime cost profile from my model. So essentially, the LCC module is a calculator that lets you take on extra cost calculations on top of what AvSim and RCMCost already do. Now, there are a couple of modules here that are similar to what Viable does. One of those is the process reliability module. I don't know if you're familiar with the concepts I guess what they call a Barringer process or process reliability analysis. Essentially, it's historical failure analysis, a bit like Viable, but instead of analyzing historical failure data, you're analyzing historical production data. So here you can see I've imported a list of capacities, a list of production levels, and then the date on which each of those production levels was recorded. That is automatically plotted as these data points on my cumulative probability plot. And I then manually mark these cusps. So anywhere where I can see the data pattern clearly changes, I can just click on it, and it creates a cusp, and then the program can break the area underneath that curve into different regions representing different amounts of lost capacity. So I can break down my capacity losses, and then I can compare that to my data, cause data, so why on a particular day did my productivity fall to a certain level, and then I can compare that to here and say, okay, well, these losses were coming from maintenance, and these losses were coming from different types of failures, and so on. So this module is letting you analyze your historical production data and try to identify the source of production losses over the life of the system. So again, this is not included with the other modules. This one is a standalone tool with its own license. Another tool like that is the accelerated life testing tool. I will open again an example. No, bear with me for a moment. Okay. So accelerated life testing, I mean, you can probably look at this and see again, it's very similar to Viable. Here, where Viable generally works by fitting failure data that's been collected in the field from a functioning system, the accelerated life testing module lets you analyze test data. So maybe there's a piece of equipment that you have that has a very high mean time to failure. So it's difficult to do a Viable analysis because you don't have much failure information. So instead, what you might do is take a population of these equipments, put them under very high stress to make them fail, record how long those failures took, and then from that, and knowing how much stress you placed on the equipment, you can extrapolate what the actual mean time to failure would be if you actually use this equipment in the real system. So basically, the principle is the same. I can provide the program with a list of times to failure, but now I need to tell the program the stress profile. So basically, how does the equipment, how is it expected to respond to stress, and what kind of stress am I placing the equipment under at each stage of testing? And the program from that can extrapolate things like the mean time to failure. So ALT, the accelerated life testing, and the process reliability modules, again, they're both separate licenses. The other thing is that unlike Viable, these modules don't really talk to the other modules. They're separate analysis tools, part of Availability Workbench, but they don't link to AvSim or to RCMCost, whereas the Viable module does. I suppose that the last thing to say is, if you are using an ERP system, something like SAP or Maximo, there are portals available for those systems. So if you want to build, say, an RCMCost project based on data you're storing in SAP or in Maximo, you can do that. So you can link to those systems through the portals, download that data, and use them to build your RCMCost project. You can also upload data back to your ERP system, though I know a lot of our customers prefer not to do that, but that is an option that's available. So that's basically everything that's in Availability Workbench. Do you have any questions at all about anything that we've looked at this afternoon?
Well, I asked already. I don't know, you?
I'm fine.
I think I will try again with this explanation. Try to compare that we usually do and check if this software is for us. I need to talk also with my boss to explain her all these new capabilities and to project their use in our daily work.
Okay. Well, if you... Sorry, go ahead.
It's very interesting. There is a huge capability, so thank you for the explanation.
No problem. I'm going to, once the meeting is finished, I'll produce the video and I'll send you a download link for that. And otherwise, if you do think of any more questions in the next few weeks, please feel free to get in touch. If you have technical questions, you can contact me. If you have any questions about licensing or about prices, then I think you've been in touch with Rachel. She will be the best person to speak to.
Okay, yes. We have already the return of Rachel about the license price.
Okay. Again, for any technical questions in the future, you can just get in contact with me. But again, I'll send you the video later today.
Thank you.
Thanks.
Okay, no problem. Thank you very much for joining me this afternoon, and enjoy the rest of your day.
Yes, you too.
Thanks. Have a good day.
Bye-bye. Bye-bye.
Bye.